What is a logistic regression? How is it calculated? And most importantly, how are the results interpreted? That's what we will discuss in this video. This is the last video in our playlist on regression analysis. Let's start with the first question. What is a regression? In a regression analysis, you want to infer or predict an outcome variable based on one or more other variables. The outcome variable is called dependent variable and the other variables independent variables. Okay, so what about logistic regression? A binary logistic regression is now a type of regression analysis used when the outcome variable is binary, meaning it has two possible values like yes or no, success or failure. Let's look at an example. Let's say we are researchers and we want to know whether a particular medication and a person's age have an influence on whether a person gets a certain disease or not. So the outcome we are interested in is whether the patients developed the disease or did not develop it. And our independent variables are medication and age of a person. Now, with the help of a logistic regression, we want to infer or predict the outcome variable based on the independent variables. Okay, but what is the difference between a linear and a logistic regression? In a linear regression, the dependent variable is a metric variable, e.g. salary or electricity consumption. In a logistic regression, the dependent variable is a binary variable. So, with the help of logistic regression, we can determine what has an influence on whether a certain disease is present or not. For example, we could study the influence of age, gender, and smoking status on that particular disease. In this case, 1 stands for diseased and 0 for not diseased. We now want to estimate the probability that a person is diseased. So our data set might look like this. Here we have the independent variables and there the dependent variable with 0 and 1. We could now investigate what influence the independent variables have on the disease. If there is an influence, we can predict how likely someone is to have a disease. Okay, but why do we need logistic regression in this case? Why can't we just use linear regression? A quick recap. In linear regression, this is our regression equation. We have the dependent variable, the independent variables, and the regression coefficients. However, our dependent variable is now binary, taking on the value of either 0 or 1. Regardless of the values of the independent variables, the outcome will always be 0 or 1. A linear regression would now simply put a straight line through the points. We can now see that in the case of linear regression, values between minus and plus infinity can occur. However, the goal of logistic regression is to estimate the probability of occurrence. The value range for the prediction should therefore be between 0 and 1. So we need a function that only takes values between 0 and 1. And that is exactly what the logistic function does. No matter where we are on the x-axis, between minus and plus infinity, only values between 0 and 1 result. And that is exactly what we want. The equation for the logistic function looks like this. Logistic regression now uses the logistic function. For that, the equation of the linear regression is now simply used. This gives us that equation. This equation gives us the probability of the dependent variable equal 1 given specific values of the independent variables. What does this look like for our example now? In our example, the probability of having a certain disease is a function of age, gender, and smoking status. Next, we need to determine the coefficients that help our model best fit the given data. This is done using the maximum likelihood method. For this, there are numerical methods that can solve the problem effectively. A statistics program such as DataTab therefore calculates the coefficients. Alright, let's work through this example on how to calculate a logistic regression and then look at how to interpret the results. To calculate the regression, we just go to datadep.net and copy our data into this table. If you like, you can load the sample data using the link in the video description. We want to calculate a logistic regression, so we just click on Regression. We choose disease as the dependent variable and age, gender and smoking status as the independent variables. Datadep now calculates a logistic regression for us. Depending on how our dependent variable is scaled, Datadep will calculate either a logistic or a linear regression under the tab Regression. Since we have two categorical variables, we can set the reference category. We will just use female and non-smoker as reference. Now we can choose for which category we want to build the regression model, so we can decide if we want to predict if a person is diseased or not diseased. Instead of diseased and not diseased, we could of course also have 1 and 0. Okay, before we go into detail about the different results, a little tip. If you don't know how to interpret the results, you can also just click on Summary in Words. A logistic regression analysis was performed to examine the influence of age, gender male, and smoking status smoker on the variable disease to predict the value diseased. Logistic regression analysis showed that the model as a whole was significant. And then comes the interpretation of the different independent variables. Further, you can click on AI interpretation at the different tables. We will now carefully go through each table step by step to ensure everything is clear to you. Let's begin at the top. First, we get the result table. Here we can see that a total of 36 people were examined. With the help of the regression model, of these 36 persons, 26 could be correctly assigned. That is 72.22%. Next is the classification table. This table shows how often the categories not diseased and diseased were observed and how frequently they were predicted. In total, not diseased was observed 16 times. Among these 16 individuals, the regression model correctly classified 11 as not diseased, while misclassifying 5 as diseased. Of the 20 diseased individuals, the regression model misclassified 5 as not diseased and correctly classified 15 as diseased. But how do we determine whether a person is classified as diseased or not? As mentioned earlier, logistic regression provides the probability of a person being diseased. So we obtain values ranging from 0 to 100%. Now we simply set a threshold of 50%. If a value exceeds 50%, the person is classified as diseased. Otherwise, they are classified as not diseased. Of course, you can choose a threshold other than 50%. To learn more about this, check out our video on the ROC curve. So let's have a look at the next table. The chi-square test evaluates whether the model as a whole is statistically significant. For this, two models are compared. In one model, all independent variables are used, and in the other model, the independent variables are not used. Now we can compare how good the prediction is when the independent variables are used and how good it is when the independent variables are not used. The chi-square test now tells us if there is a significant difference between these two results. The null hypothesis is that both models are the same. If the p-value is less than 0.05, this null hypothesis is rejected. In our example, the p-value is less than 0.05 and we assume that there is a significant difference between the models. Thus, the model as a whole is significant. Next comes the model summary. In this table, we can see on the one hand the -2 log likelihood value, and on the other hand we are given different coefficients of the determination R squared. R squared is used to find out how well the regression model explains the dependent variable. In a linear regression, the R squared indicates the proportion of the variance that can be explained by the independent variables. The more variance can be explained, the better the regression model. In a logistic regression, however, its interpretation differs and multiple methods exist to calculate R squared. Unfortunately, there's no consensus yet on which method is considered the best. DataDep gives you the R squared according to Cox and Snell, according to Nagel-Kerke, and according to McFadden. And now comes the most important table, the table with the model coefficients. The most important parameters are the coefficient B, the p-value, and the odds ratio. We'll now discuss all three columns. In the first column, we can read the calculated coefficients from our model. We can insert these into the regression equation. So we get the coefficients for age, gender, smoker, and the constant. For example, for a person which is 55 years old, is male and is non-smoker, we get a probability of 36%. Thus, it is 36% likely that a 55-year-old male non-smoker is deceased. In reality, there would certainly be many other and different independent variables. Okay, but what about the p-value? So, the p-value shows whether the corresponding coefficient is significantly different from 0. In other words, it tells us if a variable has a real influence or if the result could just be due to chance. If the p-value is smaller than 0.05, it means the difference is significant. In our case, all p-values are greater than 0.05, indicating that none of the variables have a significant influence. And finally, the odds ratio. But what are odds and what is the odds ratio? Let's start with the odds. Let's say we have two possible outcomes of something, success and failure. For example, if a therapy is successful or not. Let's say that the probability that the therapy is successful is 0.7, so 70%, and thus the probability of failure is 1 minus 0.7, so 0.3. Okay, but what about the odds? Odds are defined as the ratio of the probability of success and the probability of failure. Or in other words, odds represent the ratio of the probability of an event happening to the probability of it not happening. If we look at our example, the odds are 0.7 divided by 0.3, which equals 2.33. This means the event success is 2.33 times more likely to happen than not. So odds give us a measure of the likelihood of an event happening versus it not happening. In this case, we've calculated the odds of success. Of course, we can also calculate the odds of failure. Alright, now that we understand odds, let's talk about odds ratios. So what are odds ratios? Let's look at the example from the beginning. We are studying a new medication to reduce the risk of a certain disease. So we have a group A, patients with medication, and a group B, patients without medication. Let's say in group A we calculated a probability of 60% or 0.6 of getting diseased. So the odds of getting diseased is 0.6 divided by 0.4, which is 1.5. Again, odds just represent the ratio of the probability of an event happening to the probability of it not happening. In our case, in group A, the likelihood of being diseased is 1.5 times higher than the likelihood of not being diseased. Let's say in group B, where the patients didn't get the medication, the probability of getting diseased is 80% or 0.8. So the odds in group B of getting diseased are 0.8 divided by 0.2, so 4. Therefore, in group B, the likelihood of being diseased is 4 times higher than the likelihood of not being diseased. What about the odds ratio? With the odds ratio, we can now compare the two groups. To do this, we can compare the odds of getting the disease in group A relative to the odds of getting the disease in group B. So the odds ratio is simply calculated by dividing the odds in group A by the odds in group B. This results in an odds ratio of 0.38. The odds ratio of 0.38 means that the odds of being diseased in group A are 0.38 times the odds of being diseased in group B. Of course, we can also switch the order. Then the odds ratio would be the odds in group B divided by the odds in group A. In this case, the odds ratio of approximately 2.67 means that the odds of being diseased in group B are 2.67 times higher than the odds of being diseased in group A. So an odds ratio is simply a comparison of the odds of an event occurring in two different groups. The odds ratio indicates how much more likely the event is to occur in one group compared to the other group. If the odds ratio is greater than 1, the event is more likely to occur in the first group. If it is less than 1, the event is less likely in the first group. Okay, now let's put it all together and look at how to interpret the odds ratio in logistic regression. Let's get started. First of all, to calculate a logistic regression, we need data. Let's say we have data from 50 patients. Our outcome variable is disease, which is coded as 0 for not diseased and 1 for diseased. And we have two independent variables, medication and age. Now we can use this data to calculate a logistic regression. You can find a link to the dataset in the video description. In the first column, we can see the coefficients that define our model. These coefficients can be entered into the logistic regression formula. Here we can see the coefficients from the table, the constant, the coefficients for medication and for age. Now we just need to enter a value for medication, such as 1, indicating the patient received medication, and a value for age, for example, 50. Then we can calculate the probability. In this case, the probability of being diseased is 0.55 or 55%. So for a patient who took the medication and is 50 years old, the probability of being diseased is 55%. Of course, we can simply use DataTab to calculate this probability. To do this, just enter 1 here and 50 there. We will then also get a probability of 0.55. And DataTab further gives us the odds. As we know, the odds are calculated by the probability that a certain event will happen divided by the probability that the event will not happen. We therefore get 0.55 divided by 1 minus 0.55, which equals 1.22. Okay, but we are not interested in the odds alone. We are interested in the odds ratio. Again, the odds ratio is simply a comparison of the odds of an event occurring in two different groups. The two groups could be persons who took the medication and persons who did not take the medication. Therefore, if we're going back to DataTab, we just need to compare the odds of a person who took the medication with the odds of a person who did not take the medication. So to get the odds ratio, we just need to divide the odds of a person who took the medication by the odds of a person who did not take the medication. This results in an odds ratio of 0.64. And surprise! The calculated value matches the odds ratio listed for the variable medication. The odds ratio of 0.64 for medication indicates that for individuals who took the medication, the odds of the outcome diseased are 0.64 times the odds of those who did not take the medication. Alright, with medication we have two groups to compare, But what about a continuous variable like age? In this case, we simply look at what happens when we increase age by 1 unit. For example, we might compare the odds of the outcome for someone aged 50 versus someone aged 51. This allows us to calculate the odds ratio by comparing the two odds. In this case, we get an odds ratio of 1.04. So for each 1 year increase in age, the odds of the outcome deceased increase by a factor of 1.04. But there's one thing I haven't told you yet. The odds ratio can actually be calculated simply by exponentiating each coefficient. So e to the power of 0.45 is 0.64, which is the odds ratio of medication. And e to the power of 0.04 is 1.04, which is the odds ratio for age. To sum it up, odds are simply the ratio of the probability of an event happening to the probability of it not happening. The odds ratio is now the ratio of the odds that an event occurs in two different groups. Great! Now we have a solid understanding of regression analysis, including simple linear regression, multiple linear regression, and logistic regression. As mentioned earlier, if you want to learn more about classifying categories using logistic regression, please check out our video on the ROC curve. Thanks for watching. I hope you enjoyed the video.